Gibbs free energy equation or any of those things to you. Um, so does anybody have questions for me? Okay, so Mar and Carter and all, I can't seem to unmute you. Sorry, I can't seem to mute you. Could you please?
You need to mute
make
over
sure
there.
that you're muted because the background sounds are coming through. Okay, so let's just try a couple more of these and just again for a better understanding of what these terms mean. For example,
Thank you.
let's say if I were to draw a reaction profile diagram that looked something like this. So we have energy on the y-axis, reaction coordinate. Energy can either be Gibbs free energy or enthalpy. It can be either of the two. So the reaction coordinate is on the x-axis, meaning the progress of the reaction, the time of the reaction. And energy, either it's enthalpy or Gibbs free energy on the y-axis. So let's say I were drawing a energy profile. Let me draw it first. It's, as you know, it's challenging for me to draw stuff. Then I'll ask you questions.
That's 4 steps.
Something like that. Okay. So here are the questions related to this energy diagram for any hypothetical reaction. First question I have is, how many steps
4.
are in the mechanism of this reaction? Anybody?
4.
Do you all agree? Every step in the mechanism has its own energy diagram. Absolutely. Carter is right. This is step 1. So this portion of the energy diagram is for step 1. That portion is for step 2. This is for step 3 and step 4. Do you guys all agree?
Yeah.
Right? Okay. Then the next step is the overall reaction exothermic or endothermic? Overall reaction.
Exo?
So what are you looking at? You're absolutely right. What are you?
I'm looking at the beginning of the first step and the end of the last step, and we go down over time. So that means there's
Exactly.
yeah.
You're looking at the reactants compared to the products, and this is exothermic. Everybody okay? Okay. Next question, using the same diagram. What about step 1? Is step 1 of this process exothermic or endothermic?
Endothermic?
Do you all agree? Because now you're only looking at step 1. You're looking at step 1, R going to intermediate 1. That's step 1, and absolutely that is endothermic.
How do you know?
How about step 2?
Because it's rising, it's going up. Oh, okay. Gotcha.
Also endothermic,
How about step 3?
Endothermic.
exothermic,
How
No.
about step 4?
exothermic.
So the point here is the individual steps in the mechanism can be exo or endo. So for each individual step, you're looking at that portion of the graph
So
only.
three.
But for the overall
is the
reaction,
peak.
you're comparing the
Yeah, but it's
original
exo.
reactants to the final
It's
products.
going
because
down.
because it's
Are we all
starting
okay,
to go
everybody?
down.
Okay. Next question. Using the same energy diagram. How many transition states
4.
are depicted in this energy diagram?
4
And where are they?
under the, what do you say, the area of the open curve? I don't know how to say.
In the valleys.
In the valley,
No.
thank you, yeah.
No. Transition states are never on the valleys.
Oh, no, in the,
Transition state is always
On the
peak.
top. Okay, thanks.
oh, okay.
This is transition state 1. That is transition state for step number 2. Transition state for step number 3. And transition state for step number 4. Every step has its own transition state. And remember, transition states are models. They may or may not be real things. These are really models that we create to understand how the reactant can go through the activation energy and become the product. So those are models created by us. That is why they're always on the peaks, never in the valleys. So who exists in the valleys?
The energy, or what was it called?
What is represented there? Intermediates, exactly.
Oh,
So
Intermediates.
how many intermediates are there in this entire overall reaction? How many intermediates? No, not really. Not 4.
2?
How many intermediates?
5.
By 5.
2.
Oh, wait, no.
3.
Here is your intermediate 1.
1, 2, and 3.
Here's your intermediate 2. Here's your
Because
intermediate
they're the ones in the middle, right?
Exactly.
Intermediates are in the
Intermediate
valleys.
is defined as a substance that is created.
But in the middle also, right?
It's a real
that's the
thing.
values.
But it's used up in the subsequent step. So it's made first, used later. Everybody okay?
Okay.
Okay, next thing. Next question. Can you identify the rate determining step? Which step, 1, 2, 3, or 4, is the rate determining step?
Number 3.
And why is number 3 the rate determining step, Carter? Or anybody?
It's at the peak.
The longest.
What do you mean by that? Let's be clearer in our definition.
It's-
Why is number 3 the rate determining step?
It's the longest.
It has most activation energy.
It has the highest activation energy. It's not about how high the peak is or how low the peak is. That's irrelevant. It really depends on the activation energy. And activation energy is the energy difference between the reactant of a step and its transition state. The biggest activation energy is the slowest step. The slowest step is the rate determining step. So if you're looking at the activation energy, this is activation energy for step number 1. This is activation energy for step number 2. And that's for step number 3. And here is the activation energy for step number 4. Then whichever step has the biggest activation energy is the slowest step, which means it is the rate determining step.
I didn't know that it was, like, I don't know where to put the, okay, like, for example, in number 1, activation, I would have cut it off at I1, and on I3, I probably would have gone all the way down to products. I just wanted
Then you're
to,
wrong. Then you're wrong.
yeah, why?
Activation energy is defined as the energy needed for reactants to become transition state. in an energy diagram, it is always the energy that is needed for the reactants to get to the peak. That is, so it's always the difference between the energy of the starting point
Well,
and the transition state. That is activation energy.
so in number 1 up above, isn't R where we, oh yeah, yeah. Oh,
I did.
okay,
Yeah,
yeah, you did. Thank
absolutely. You're absolutely right. Everybody okay? And of course, the overall reaction was exothermic because for that we are looking at the difference between the energies of the reactants and products. If that is negative, then it's exothermic. If that is positive, then that's endothermic. Is everyone okay with me? Or with this? Of course you're okay with me. I assume so. Questions? Understanding the concepts, understanding the terms. Okay, then let me write a mechanism. Again, don't focus on the mechanism. I'm not going to ask you to write mechanisms. We are not there yet. That's what we start doing next quarter. But let me write a mechanism, and then I'll ask you some questions based on that mechanism, okay? Oh, shoot. So, there it is. Give me a second, I'm thinking. Okay. One. Two. Three. Five. So this is a mechanism that I have written, 5 steps in the mechanism. Okay, well, I'm just going to write this part again, make it a little bit clearer. It is kind of squished over there. Come on. Sorry, that's wrong. Okay, so I have, based on this mechanism, I'm going to ask you a few questions. You guys ready? First question. What is the overall reaction equation?
That would be,
Remember, mechanism tells us what steps does reactants go through to become products, right? That's what this is saying. Well, It has to go through steps 1, 2, 3, 4, 5 in order to become the product. So what is the overall reaction equation?
The first reactant in the last product.
Is that right? Are you sure?
Plus
No, not
CH3OH.
Good. So what we are doing here is we are adding all the equations, canceling out things that are on either side of the arrows. So do you all agree that the overall reaction is going to be the alcohol? Is there another reactant here? Is there something else that does not get cancelled?
CH3OH.
That's a reactant. It reacted with the carbocation in step 4, so it's a reactant. Any other reactants? Okay, what are the products or product? Oh, excuse me. Any other? Oh, what are the products?
The structure with the OCH free on it.
And
At the
ether?
end with plus H plus.
Is H plus really going to be a product? You're right, this is definitely a product. Is H plus a product?
Probably not.
Doesn't this H plus get cancelled by that H plus?
Oh yeah, okay. Okay.
So no, it's not a product.
Yeah.
Agree. Everybody okay? That's your overall reaction equation?
Am I missing an H2O, or did I just not see something?
Oh yes, you are not missing an H2O. I didn't write it because we Ochemists are so lazy. Where would we put the H2O, Eric?
On the product.
Where? Okay, good, yes. In which step of the mechanism was H2O produced?
Oh, 2.
Yeah, absolutely right. Absolutely right. So yes, you're right. H2O is a product. Are we all good, everybody?
I'm kind of lost.
Okay. Next question I have for you. What kind of reaction is this overall reaction? Is it substitution, addition, elimination, rearrangement, or maybe a combo of a couple of them?
Don't we need to go back
Is
one?
it substitution because we're substituting the CH3OH with the OH? Oh wait, oh I lied.
No, you are right. We are substituting. We did somehow got rid of that and we brought that in. So it is definitely a substitution. But is it pure substitution or is it substitution with something?
Is it rearrangement?
Why do you say that?
Because the OH, the OH and the OCH free
What?
move spots.
Meaning
It happened.
they are
It happened somewhere unexpected.
and the carbon skeleton changed as well.
Yeah.
Right? Exactly. You're absolutely right. It is substitution with rearrangement. The reaction happened at a different spot than what you expected it to, and the carbon skeleton changed as well. Is everybody recognizing that? Good. Next question. Are you guys ready? Yes, Jasmine, you're right as well. I just am not good with keeping my eye on the chat message, but I will try better. Next question. What is the role of this compound? What is it behaving as? What would you label it as? In this reaction, what is its job?
Is it a reactant?
Good. Everybody agrees? Right? And of course, that's also a reactant. Products Well, that's a product. And this is a product as well. We all good over there? Oh, good. Okay, I wasn't going there yet, but I will go there soon, now that you've given me an idea, Gavin. Okay, next question. What is, or how would you label these substances? Let me circle them, then I'll ask you. How would you label this guy? What is that? It's an intermediate because it was created in step 1 and used up in step 2. Do you guys agree? Yes?
Yep.
Okay, if you guys agree with that, then what is the role of this guy? What is that?
Is that also an intermediate?
Also an intermediate. It's created, that's the second intermediate. Created in step 2, used in step 3. What about this guy? And this guy, so on. What are they? They are all intermediates. Definition of an intermediate is something that is created in one step of the mechanism, but then used up in a subsequent step of the mechanism. So how many total intermediates in this mechanism?
4?
Everybody agrees?
No, I'm not.
What's the total number of transition states in this intermediate, in this mechanism?
5.
5. Every step has its own transition state. Every step has its own transition state. Can you tell me in which step of the mechanism did the actual rearrangement take place? Which step of this mechanism shows the actual rearrangement?
Step 3.
Step 3. Exactly. Step 3 is where a methyl group moved and to a different position and changed the skeleton of the substance. Everybody sees that? Okay. Next question. If I were to, well, that's kind of a given. If I were to tell you that step 2 is the rate determining step, don't ask me why, just take it for now. Which step will have the highest or the largest activation energy?
Or 2. 2, right?
Yeah.
Step 2. Rate determining step is the slowest step, which means has the highest activation energy. Great. Now let's ask the question that Gavin was hinting at. Can you just focus on step 1? Just focus on step 1. Can you tell me what is the role of the reactant alcohol? What is the reactant alcohol behaving as, reacting as in step number 1?
Electrophile?
Not really.
Nucleophile?
Is it a base/nucleophile?
Just use one term.
Nucleophile?
It can't be both, but it can be either. Which one? Is it going towards a proton or is it going towards an electrophile?
It's a proton. It's going for a proton.
Then we call it a base. It's a base. Everybody okay?
Taking a product.
So then what is
It's
the
accepting a
role
product.
of methyl alcohol in step number 4? What is methyl alcohol behaving as, reacting as?
Electron
A
rich
base or
nucleophile.
an acid or an electrophile or a nucleophile?
Nucleophile. It's electron rich, right? Nucleophile.
It is the nucleophile.
Oh.
Absolutely. So what is this carbocation in step number 4 reacting as?
As a,
Electrophile?
no, acid.
Absolutely.
Oh, really?
And of course, that's the acid.
Oh, okay.
Acid reacts with the base reacts with acid. Nucleophile reacts with electrophile reacts with nucleophile. Is everybody seeing those things here? Can you then tell me what is the role of this intermediate in step 5 or reactant in step 5? What is it reacting as?
Electrophile.
Chemically, what is it reacting as?
Electrophile?
An acid?
It's giving a proton.
Oh.
If it's going to give a proton, then it is an acid, exactly. So for us from now on, when we talk about an acid, anything that gives a proton is an acid. Anything that takes a proton is a base. Anything electron rich going to other electrophile is a nucleophile and vice versa. Everybody okay?
Just to be clear, can it be electrophile at the same time of base or acid, or not?
No, not.
Or no?
The role is different. Acid involves proton changes. So if it's giving a proton or taking a proton, that's when you use the terms acid bases. With electrophile nucleophile, we are not talking about Lowry-Bronsted acids. So no.
What are we talking about?
We're talking
Any
about
other
Lewis
questions?
acids.
With the nucleophile.
Now I want to ask you, if you understand what's going on so far, can you clean it up a little bit?
Electron rich or
One
electron poor?
substance we did not
Yes.
yet talk about in this mechanism, and that is H+. H+ is neither a reactant nor a product, right? When you wrote the overall reaction of equation of this process, H+ cancelled out. So it's neither a reactant nor a product. So what is it?
Catalyst.
Is it an intermediate? Can you call H+ an intermediate?
I think Gavin answered on the message.
No. Intermediate is created first, then used up. H+ was not created. We used it first and then created it later on in the mechanism. And that is why, absolutely, Gavin, that is a catalyst. You must have heard of the term catalyst. A catalyst is something that speeds up a reaction, right? Isn't that what you guys learned? A catalyst is a substance that is added. We start with it. It goes in the start of the reaction. So it is added to speed up the reaction, make it go faster. And the difference between an intermediate and a catalyst is that a catalyst will be used first and recreated in a subsequent step of the mechanism. An intermediate is created first and then used. A catalyst is used first and then created again, so it cancels out. It goes in and it comes out, theoretically unchanged. Does everybody understand that? Now, here's also the most important thing. How does a catalyst speed up the reaction? What does a catalyst do to make the whole reaction go faster? Anyone? What does a catalyst do? Actually not, and that's what I wanted to emphasize on.
Lower?
A catalyst does not lower the activation energy of the original
Increases.
process. What it does is it provides a different process, a different mechanism for the reactants to become products that overall has a lower activation energy. Does that make sense? And that's really the key here for us to understand, because that's a very common misconception. And your biological systems have a lot of catalysts. Enzymes are catalysts. So catalyst does not lower, so for example, just to emphasize and make sure everybody understand, that if you have an energy profile, let's say reaction becoming product, the catalyst does not lower the activation energy. It's not like it makes it go faster because the activation energy goes down. No, not really, not at all. The catalyst provides a different pathway for the reactants to become products, which overall have lower activation energy. So it may go differently, and overall activation, the rate determining step activation energy is lower than what it was before. So please do make sure you understand this subtle difference, because it's actually pretty critical if you are going into biochem or even biology for that matter, that catalysts do not lower activation energy. They give us a different way to achieve the reaction, which has lower activation energy. Exactly, like a shortcut. You're right. Perfect. Does that make sense, everybody? Okay, so that's all I had to say about chapter 6. As I was saying in class on Monday, there's a lot more in the book. In chapter 6, we are not doing any math in regards to the delta G's and equilibrium constants and so on and so forth. Our goal here is to understand what these terms mean, so that next quarter when we start, we can actually use these terms, because we will look at mechanisms of different reactions, and we'll talk about the kinetics and blah blah blah. So we should at least be able to process that information. Can I answer any question for chapter 6?
Did you say that it provides a shortcut for them to become products, right? Is what you said?
Yeah, exactly. And that's
Okay.
what you said, right? No, that was not you. That was who? Yeah, that was you.
Yeah.
Exactly. That provides a
Okay.
shortcut, which is a different path. It's not the same path. You're just doing it faster.
This one's giving
No,
a
no, no.
proton, right?
It's providing
I mean,
a
it's
different
receiving.
path, which
No,
goes
no,
faster.
It's electron.
Absolutely.
It has an electron deficit.
Okay, so that is chapter 6. Again, just focus on the parts that we did talk about. Please don't go into the details of things that we did talk about. I was also hoping maybe we could do a couple of these problems that we skipped on Monday. Or are you guys good? You don't need it, you got it. So we can just stop right here. What do you guys think?
I would like to.
Okay, this is the carbon NMR worksheet. The front page, I think, look like that. So let's work on a couple of these. So here is an example where you have an IR, you have a proton NMR, and a carbon. So how do we solve this? First of all, IHD. I think without even thinking, IHD, because it's so useful in my opinion. Can someone tell me what is the IHD for this compound?
Oh, right. Well, where? Oh, here it is. We dropped the O.
Four IHDs.
I heard 4. Can someone confirm? Yes? Okay, what do we... Sorry.
No, isn't it?
What do we say when... No, it's not 4. It's not 4. Is it 4?
I got 5.
Oh,
Yeah, I was gonna say.
okay, thanks.
Half of C10H22. 2n plus 2
I did C10H14.
minus C10H12.
I did C10H14.
Oh, okay.
Okay. So what do we say
Yeah, I was
whenever
trying to figure out. I was like,
IHD
where am I
is
wrong?
4 or above? As a hint. It may,
Benzene ring?
say that again, please.
Benzene?
You should think about it. Exactly. It may or may not be. That's a different story. But let's at least think about it. So where would we get the confirmation from? where would we get a confirmation that maybe there is benzene? Well, this part of the proton NMR. This part of proton NMR is specifically for benzene hydrogens. And since we see signals there, we can say, yep, there is benzene. Is everybody okay?
Yeah.
Okay. Then let's look at IR. Let's see what information we can get from IR. Please go ahead, tell me, what is IR telling us?
This isn't the IR, but for the benzene, because we know there's 5 hydrogens, does that mean it's mono-substituted?
Yes, exactly. And we will get there, absolutely. You're absolutely right. What Dash is saying, if you look at the benzene signals, there are 2 of them, actually 3, but 2 of them are very close. And the total integration is 5 hydrogen, which kind of means that it is a mono-substituted benzene. Absolutely right. Absolutely. Okay. What about IR? What is IR telling us?
C double bond O at 1,7.
Okay, good. 1007 C double bond. Oh, good.
I got an aldehyde in there as well.
Actually, I'm not seeing an aldehyde, but why are you getting an aldehyde?
Well, I'm looking at the, like, between 28, I think. Well, let me see. Yeah, like, between 28. Oh, never mind. My bad. Yeah.
Aldehyde CH is very specifically one between 27 and 28, and the other 28 and 29. So this one has between 28 and 2900, but it does not have one between 27 and 2800, right? Do you see that?
Yes, I do. Sorry.
No, don't be. You don't have to say sorry. I just want to make sure you're also noting that part.
Is there also sp-free hybridized carbon hydrogen bonds?
So so you did say, sorry.
I thought we had that one already.
You said this is C double bond O, okay. What signals are being shown by those, what bond is being shown by those signals?
SP2 CH. Oh,
SP2?
SP2 what?
CH1?
Exactly. Please remember, IR does not show atoms, IR shows bonds. So you got to show the bonds. And Carter, you're absolutely right. Those signals are due to sp3 carbon-hydrogen bonds. Okay. Is there another signal that might be
at
useful?
1275, could that be a CO
Yo, single bond.
single
Absolutely.
bond?
Would it be the 700? The 9
What is that
signal?
Benzene or what?
Benzene?
What kind of benzene is that indicating to us?
Isn't it like a different kind of benzene? That's what I have in my notes.
What do you mean by different?
Would it be like not a hexane?
Benzene is not a hexane no matter what. Oh, this benzene is 6, so there's only one kind of benzene. So what is that signal indicating? Isn't that also, and I don't have this table in front of me, but isn't that also indicating a mono-substituted benzene?
Yeah, yes.
Yeah, somebody said it in the chat.
Oh, sorry, I can't see anymore. Exactly. It's mono-substituted benzene, which we have confirmation for from NMR. So these are the main signals. Of course, there are carbon-carbon double bonds right there, but these are the main signals from the IR. Is everybody okay? Everybody okay? Okay, since I'm annotating on the screen, I just realized probably not the best idea. I have to erase this stuff so I can go to, but yeah, not the best idea. I will do that next time. Okay, let's now look at proton NMR. So for now, we know that we have the following. We have a mono-substituted benzene. We have a C double bond O. We have, so I'm just going to write those down here.
5, 6.
We have a mono-substituted benzene. we have a C double bond O. We also have a C single bond O. We have sp3CH, sp2CH. Okay, cool. Now let's look at proton NMR. What is that telling us? So first of all, going left to right, I'm just going left to right. There's no reason why, but so do we all agree these are explained because we have a monosubstituted benzene? Okay, now let's look at the other signals. So we have a signal for 3 hydrogens, that's probably a methyl of some kind. We have a signal for 2 hydrogens, a methylene, and another methylene over there. But look at the multiplicities. The methyl is a triplet. Methylene is 1, 2, 3, 4, 5, 6. It's a sextet. And the second methylene is a triplet.
Oh, we have an.
Does that give us a hint?
Yeah. What is it?
Propyl group?
Group, exactly. So, let's look at the pieces we do have so far. We have the monosubstituted phenol. We have
CH2,
C double bond O and C
YL?
single bond O
YL.
as well. We have a propyl group. How many carbons, how many hydrogens, how many oxygens are
1,
used
2,
up?
3, 4,
How many
5, 6.
IHDs are used up? What is left? Anybody?
9 carbons, 2 oxygens.
Sure, 9 carbons? No.
Oh, 11 carbons.
But we had only 10 carbons to start with.
Oh,
How can we have it? No, that's a good point. I wanted to actually raise that point. I wanted to ask you guys about that point. We had only 10 carbons, then how do we have 9 carbons? Is there something we might want to modify here? Suggestions?
The C bonded to O?
What? Go ahead. What do you want to do with that?
Could you just, I don't know, could you just consider it the
1,
C
2,
double bond
3,
O
4,
as a
5, 6,
signal?
7, 8,
Exactly.
9,
That's not a
10.
separate piece.
It's
That's
a
not a
ester.
separate piece. It's part of the C double bond O group. Exactly. Now if you add up all your atoms here, do we have 10 carbons? Yes, we do. How many hydrogens do we have? 7 plus 5.
2,
is
4,
12.
7, 8,
How many
9, 10,
oxygens?
11,
2.
12.
We've accounted for all atoms. How many IHDs accounted for here?
1, 2, 3,
Anybody? How many IHDs accounted
4,
5 with the benzene.
for?
5.
4 in the benzene. Benzene is 4.
And the 5th one is the C double bond O.
Exactly. So we've taken care of everything. So these are the 3 pieces we have. We need to put these 3 pieces together and make a molecule. So go ahead, give me a suggestion. I'm starting with benzene. What should I?
You,
Oh, that would be the O. I think the O.
Anybody?
C double bond O and then an O.
Okay, so Eric is saying C double bond O,
Yeah, and then
O, and then comes propyl.
The propyl group. That's okay.
Was there another way you could have put these
That's what I
pieces
got.
together? Could you have connected it to O, C double bond O,
oh yeah.
H2CH3? 2 possibilities, right?
Wouldn't show in a chemical shift though?
Good.
Proton.
Good. Go ahead. Can you elaborate on that thought, Dash?
Well, because it's bonded to, well, it's directly connected to oxygen, Would that move it more to the left, or
By it.
Yeah.
the benzene signals, the three that are kind of really close together?
The first,
Benzene signals may not be the easiest to pick. There's an easier signal to pick to make the decision.
The 4 to 4.5 hydrogen signal.
So you're talking about, Eric, you're talking about this signal, right?
Yeah,
So what does that indicate?
that suggests that the methyl or group is bonded to an O.
OCH2.
This guy is expected to have a chemical shift of about 4 or above, because it is connected to 4.3 here in this case. It is connected to the oxygen. Where do we expect that triplet to be if it were the second structure? Where would we expect the triplet for that same group to be at?
well, by the O.
Would that be closer to 2.5 or 2.7
Oh,
or something
I
like
see
that?
what you mean.
So, very conclusively looking at that signal, we can say that the correct structure for this compound is the first one. Everybody agrees to that? Okay. Now, something that I do, which you need to also focus on, assign signals. I mean, I always ask, and we do that in class also, assign your signals. Basically, what we are saying is, well, that methyl hydrogens are giving us this signal. This methylene hydrogens are giving us that signal. This one is right there. And then what about the benzene signals? Which signals are being shown by those hydrogens? Anybody?
Yeah, upper 2.
Should they be more shielded or de-shielded?
Shielded. De-shielded?
They should be more de-shielded because of resonance.
Oh, because it's that way. Okay, yeah.
So those two hydrogens are showing up there, whereas these three hydrogens, they are showing up here. Of course, those are so close to each other that they couldn't separate from each other, but that's why they've been clubbed together. Everybody okay?
Mm-hmm.
What about carbon NMR? Let's assign signals for carbon NMR. So, where are those?
Ouch. 1.
So, would you agree that this carbon is giving us that signal right there? This carbon is probably giving us this signal. This carbon there, right? Please notice that is just CdCl3. That's the solvent. We are not interested in the solvent. Okay. Now, yes, go ahead.
So on a test, how would you prefer us to label these? Would you want us to like letter them and then put it next to the compound, or draw arrows? What would be the best way?
Whichever way you want to, as long as I am able to see that, oh, they've connected this atom to that signal. Whichever way you prefer. And I do it different ways just to show everybody that everything is okay. As long as it's clearly connecting a specific atom to a specific signal.
Okay, could we write like the wave numbers?
Let's do that. Let's do that. Absolutely. Whatever works for you. Whatever you prefer, however you prefer to do it. So let's do that. So, where is A showing? Well, that's A. How about B? B. How about C? But the point is, we are we are connecting the atoms in your structure to the signals. Not generally based on the table that you're following. No, that's not what the question is asking. The question is asking in a very specific way, once you have a structure, where is the signal for each specific atom? Okay, now let me ask you, because this is the one a lot of you missed in your quiz, which I was going to hand back today, but unfortunately I'm not there. I will definitely give it to you the next time I see you. Guys, where is this signal showing?
160, the one a little past 160.
That signal is actually very useful, very important.
I didn't miss it.
That signal is the
did
C
not
double
do.
bond O.
I
C
know I
double
didn't miss
bond
it.
O's show to the most left of the carbon NMR spectrum, 160 or beyond. They can even be 220, depending on what kind of CO it is. That signal a lot of you missed because it was so tiny. Can anybody tell me why is it so tiny?
There's no hydrogens.
Exactly. In carbon NMR, there is no integration. But if there are fewer hydrogens, the signal is smaller. If there were more hydrogens, the signal would be bigger. So C double bond O signal is very characteristically small because there are no hydrogens on it. So don't miss it. It's important. Okay, now, what about this carbon,
Benzene.
E? How about F? How about G? And how about what comes after G?
H.
G, D, E, F, G, H. H, I. So where is signal E? So I'm going to ask you this
CC.
question. Is it supposed, would you expect it to be big or small? Two questions to decide that. How many carbons are E's? How many carbons are E?
1.
One. One. So if it's one carbon, okay, it should be very big. Does it have any hydrogen on it?
Yes. Yes. Right?
Does E have a hydrogen attached to it?
Yes.
Oh,
So should
no,
it be
Oh, no, no.
small?
No. Never mind.
dear.
I forgot.
No,
I
small.
there's a
forgot
double
Small.
bond here.
I forgot that.
Absolutely.
Freaking.
Absolutely small. So signal, this is D. This tiny thing that you see right there
Oh, I see.
is E. It's small because it's only one carbon plus it has no hydrogens on it. It's small. What about these two big ones? Compared to the others, what can we assume for these big ones?
It would be G and F.
G and F. Because they are two carbons each as opposed to one carbon for all the others. Exactly. Those two big ones are G and F.
Oh.
Good. Can we decide which one is G and which one is F?
I can't tell. Oh, well, maybe, I don't know. One is closer to E.
Which
No,
one
they're
should
both close.
more?
Is G,
Sorry. Say that
Deshielded.
again, Camilla.
is G the first line and then F the second line?
Because F is more deshielded because of resonance. The ortho position or the two position is more deshielded because of resonance through that C double bond O.
Wait, F is more
And
deshielded?
therefore, which carbon is giving us this last signal? That is H. Does that make sense, everybody? So whenever,
I'm-
oh, sorry, somebody said something.
I said something. I feel like the deshielding information between the H NMR and the C NMR is not exactly consistent.
It is consistent. Why is it not consistent? It is.
H is less okay, so in the HNMR, the H part of the benzene ring is less shielded, or less de-shielded. So it's whereas in the CNMR, the H part of the benzene ring is more de-shielded because it's further over. So that I find confusing.
Okay, let me draw this out first before we go. So, these hydrogens, because of resonance going out from the benzene ring to the C double bond O, they are more de-shielded because there'll be a positive charge on that carbon, are those. Right? You're
Yep, I feel that. Yeah, I feel that.
Yeah, you're talking more about G and H. So you're
Yeah, well,
but you're talking about, I'm just going to color coordinate so we can look at them separately. Stop it, Sunita. There we go. You're talking about this hydrogen versus these two hydrogens.
Oh,
yeah, but one is, yeah, in effect, although obviously we're measuring carbons versus hydrogens here.
I got it, Eric. I'm going to ask you this question now. When you look at this mess of signals for integrating for 3 hydrogens, I'm sorry, it has everything written all over it because I can't. There we go. There we go. When you see this signal, first of all, I hope you're all seeing that it's not a simple multiplicity.
complex.
It's not just doublet or triplet or quartet or whatever because that hydrogen should be a triplet of a triplet, and these hydrogens should be a doublet of triplets. Okay, so let's imagine this. Let's try and picture this in our minds. A triplet of a triplet is a lot of lines. A doublet of a triplet is also a lot of lines. And then on top of that, this lot of lines and this lot of lines are on top of each other. So the point I'm trying to make is, when you're looking at a complex signal like this one, how am I to tell where is that last singular H and where are those two equivalent H's? I can't. So the expectation is, my expectation is, the resonance criteria for carbon NMR does not change. It's exactly the same. So my expectation is that these hydrogens that are equivalent for two, the hydrogens that are equivalent to each other should be more shielded compared to that singular hydrogen because of resonance. That doesn't change anything. And I understand that I'm writing all over it and I'm making a real mess of all of this. So if you're all okay with it, I'm going to clean it up and do something else here. Okay, let's clean it up. So here is what I think is going on. When we are looking at that structure, is it okay with everybody if I just got rid of this part, just to make it easier on us, and not have to, worry about it for now? There is resonance that kicks towards oxygen. So when that happens, that carbon becomes positive. But it can keep going. Now this carbon is positive. And we keep going. And this carbon becomes positive.
Oh, it's the alternating thing.
Exactly.
Thank you.
Exactly. So if you look at the hybrid for it, right, in this example, because there's a C double bond O over there, and you're looking at the hybrids, whether you're looking at proton or carbon, regardless of that, these and this are going to be more de-shielded because they end up with positive charges. On the other hand, the meta ones, or these ones, never get a positive charge. So these are going to be relatively more shielded. How do I spell shielded? What's the correct spelling of shielded? Is it EI or IE? Okay, I guess. Is that correct? Anyways, you got the point. So the point is, Eric, first point is resonance, whether you're looking at proton or carbon or IR or mechanism or whatever, doesn't matter. Resonance is resonance, period. And then when you look at all the resonance structures, it is the ortho positions, this position and this position, and the para positions that get a positive charge. So they will be more de-shielded relative to others. Does that answer your question?
Fantastic, thank you.
Yeah. Guys, any other questions? Does this make sense, this whole process? Is F more Oshu? Now I don't, Jasmine, I hope your question was answered because I don't know what F is anymore. Was your question answered?
Yes.
Good. How about you, Jasmine? Yes? Oh, cool. It was answered. Okay, good. So, how do we feel, guys? Do we want to do another one or we got it? And you want to do the rest on your own and have some of your own fun?
No, we'll have our own in.
Okay, let's try this actually.
We'll have our own in the exam.
Because we're making a specific note of something called long range coupling.
Yeah.
C5H8.
Let's try this out. What is the IMF? Oh, did I just say IMF? I said IHD.
IHD.
Thank you. What is the IHD?
Okay, 5 times 2, 10 plus 2, 12. Okay. See?
1? No, I don't think so. Isn't it half of?
It's 4. It's 2, sorry.
It's
2.
3. It's 3.
No, not 3.
Not 3?
It's 2.
Guys, why?
I can't.
C5H12 minus 12 minus A is 4.
it
5 by
is
2 is 2.
I forgot to count.
Can it be benzene? Should we even think about benzene? No, not at all.
Oh, don't even think
Okay,
about it.
cool.
No. Also, there are no signals for benzene.
Good. There are no signals. Perfect.
Yeah, but
Okay, let's look at IR. What information can we get from the IR that is useful?
3,300.
3,300 is
NH?
sp2ch
No,
bond.
not
And
sp2ch is limited in the 3,000 to 3,100 range.
wouldn't it be N, one bond, single bond H?
But there's no nitrogen in the formula. Why would we think about NH when there's no nitrogen?
Is it SP carbon and hydrogen bond?
Exactly.
sp1ch bond.
Mar, are you seeing this? If the chemical formula is C5H8, why would you think about nitrogen or oxygen or anything?
Yes, I wasn't looking at my table. I was just guessing. Yeah. But yeah, no, you're right. I'm looking at the table now.
Okay. What about these signals right here? What are they representing? Which
Don't say
bond are they
aldehyde
representing?
because there's no
I
oxygen.
think you're really zoomed in. See that picture?
No, it can't be aldehyde because it would be at 2.7.
There's no oxygen.
Good, Iman. Good, yes.
And there's no
Camilla,
CO.
Did you say I'm really zoomed
Is that
in?
what you're saying?
There's no
I
oxygen.
can't see your whole screen. I can only see a really zoomed in part.
I'm looking at just the IR part. Are you not able to see the IR?
I can't see anything. All I see is like what looks
It looks like you're really zoomed in to me. I don't know. Maybe it's
What about
that's a
rest?
problem.
I'm going to then share again, just to see if that sets it, resets it, okay? Let me try it again, because it wasn't showing like that on my end. Okay, let's try it again.
So what did you say it was?
How's it
This
looking
one here?
now?
Yeah, oh, that one, a terminal, right?
SPCH, yeah.
Yeah, so what
SPCH
about
bond.
Triple bond.
Iman said,
2 pi
yeah,
bonds.
these signals are
Triple bond.
Three
representing
bond.
sp3 carbon hydrogen.
3 bonds.
Okay,
Have a triple bond, like at the 2200.
good. But which triple bond?
C.
CC triple bond.
So that's telling us, oh, we have an alkyne, right? Carbon-carbon triple bond. How many IHDs in carbon-carbon triple bond, by the way? How
2.
many? 2. Your 2 IHDs are used up right there.
Because you have 2 pi
Oh.
bonds.
Wait, how are there two IHDs?
What is an IHD?
Like if there's a
What is an IHD? Tell me. What does one
A ring
IHD
or a bond
mean
or a pi bond?
to us?
like if there's a
Pi
ring,
bond.
there's pi bonds and stuff.
Okay, let's be very clear.
Pi bonds and stuff.
So, no, again, don't be sorry. We are trying to make sure we clarify everything, okay?
Pi bond and ring.
So, when you see an IHD of 1, what does that tell us?
Oh, there's a
Pi.
there
One pi.
could be a pi bond,
1 pi bond or
Two
a
pi.
ring.
how many? 1 ring, exactly.
But we need
right?
4 for a ring.
So, when there's a carbon-carbon triple bond,
You can have cyclohexanes to
how
be 1
many pi
AHD.
bonds does that have?
Oh, two. Oh, that makes sense. I was. Thank
I
you.
love her.
Excuse me. Make sense?
Yes, thank you.
So it's an alkyne. There's no ring because the 2 IHDs are taken care of. Everybody okay? Okay. Let's go to the NMR, proton NMR. Now there's this note here which I will talk about in just a minute. But before that, before we go there, let's see what we have here. That's 3 protons, so probably a methyl, which is a triplet, a methylene, which is 1, 2, 3, 4, 5, 6 again. And then we have just with 1 hydrogen
Triplet.
and
Sextet.
2 hydrogens.
This is a sextet.
Excuse me.
This is a triplet. Oh, so we have again a
Right.
purple, but what's a sextet? So we have a
Everyone okay with me so far? Okay. Now, it's saying it's long range coupling. Long range coupling means that hydrogens more than 3 sigma bonds away are coupling with each other, meaning they're splitting each other. Same rule, n plus 1 rule. So when I look at this signal right here, do you guys see clearly? Do you see there are 3 lines? And then each of the 3 is split into 2. So that's really a doublet of a triplet. So there was a triplet first, and then each of the parts of the triplet was then split
So
into
it's not
2
a
parts.
sextet.
I thought that was only for benzene.
No, that's actually, and we are not doing it. We are sticking to benzene, but it can be seen actually for alkenes as well and alkynes as well. Anytime there is pi bonds involved, pi electron cloud can allow us to observe long range coupling. Now we are not spending time on it. That's why we only focused on benzene, but it's not always benzene. It's pi bonds, really.
What's
to
long
be
range?
honest. It's pi
Long
bonds.
range.
Will I have you expect you to be able? No, I won't.
Oh, thank you.
I'll stick to benzene. But since this example was there, so it's like, oh, let's try it out because it's there. But does everybody see how clearly that is a triplet split into doublets?
Yes.
So that's a doublet of a triplet.
Okay.
What about this signal right here? What's the multiplicity for that signal?
Which Which one? This one? Triplet.
It's just a triplet.
Triplet.
Oh, that one, triplet, yeah.
It just seems like a triplet so far.
And then a sextet.
Okay.
So,
So let's see what parts we have so far. We have C5H8 as, so 5 total carbons. And since we have this bond and this bond, do you guys agree that at least we can say that we have a terminal alkyne?
that's what's good.
So we at least have this part. Right? Okay. What can you say about these two? Since a methyl is a triplet and there is only one methylene out there,
Is that an ethyl?
it could be right. It is probably an ethyl. However, the ethyl is connected to CH3. Are we all okay? Okay. But this methylene is a sextet, which means it has 3 on one side, 2 on the other side.
Oh, and that's a, no, it can't be because
Dashes?
that's terminal.
Could this one, by the way, I do not know what the answer is. I'm also working on it with you. So we are all brainstorming together. Would that also be a CH2? Because if it is a CH2, then we can say that there is also a CH2 here. Yes? So those are triplets. This is the signal that's split into a sextet. But then the other one is split into a doublet of a triplet. The triplet makes sense because there's coupling going on there. How does the doublet happen?
Yeah, how does it? Do you have an idea?
Is that the long range?
Exactly. Exactly. That is the long range coupling going through the pi bonds of the
Oh, okay.
alkyne
That's what I was gonna
more than
say.
3 sigma
Okay,
bonds
okay.
away. Absolutely right. So if you notice,
Oh, I remember now.
right
Okay.
here we have accounted for with all of these pieces, the 2 pieces that we have accounted for 1, 2, 3, 5 carbon atoms and 3, 5, 7, 8 hydrogen atoms. We are done. All we have to do is put it all together. So what is the structure of the molecule? The structure of the molecule is basically that's your structure. So where is signal A? That's A. B? That's B. And this is C. So what is this 1 hydrogen for? Signal D is the alkyne hydrogen, which is split into a triplet long range coupling, small coupling, because of this is coupling with these 2 hydrogens here. So that's why that's a triplet, whereas these 2 are doublet of triplets. Exactly. Is everybody seeing it? Okay, what about the carbon assignments?
No, we have 5.
Let's do that. And since you guys don't like the arrows as much, I won't use that. So, oh shoot, I hate this. Okay. A, B, C, D, E. 5 signals. So do you guys agree that's carbon A? It's my That's my carbon B. That's my carbon C. Which one will you say is D and which one would you say is E? Anybody? Which carbon of the alkyne, in your opinion, is D and which one of the carbon of the alkyne is E?
E would be the carbon bonded, triple bonded to the other carbon and bonded the one in between.
Why do you say that this carbon is E, not D?
Because it's not bonded to any hydrogens.
Exactly, and that's why it's smaller compared to the others. Exactly. And the other one is D. Everyone okay? So to answer your question that you asked earlier, Dash, that we are only considering long-range coupling in benzene, just for our convenience. But long-range coupling can happen anytime the magnetic fields can go through the pi electrons. So alkenes show long-range couplings, alkynes, so on and so forth. We are not getting into those. That's a different story. Is everyone okay with this one? Questions I can answer? Can I raise it all?
Yes.
Okay, cool. So there's of course one more. I think you guys might want to work on it yourselves and have some fun. I don't want to grab all the fun from you. I want you guys to have a little bit
You're
of
so
that.
amazing.
Right?
Let's talk about the fun.
No, the fun. I've had enough fun in my life. I think it's time for you guys to have.
Jeez,
So that's it
sharing
basically. For this
completion.
quarter, we are done. Next quarter, of course, we'll start chapter 7, as we were saying the other day on Monday. Our goal from chapter 7 onwards will be, we will study one family of compound at a time. We will look at different reactions to them, mechanisms, all of those things. We get into a little bit more details of that. So chapter 7 onwards, we'll start next quarter. Can I answer any questions on the content this quarter? And yeah, we'll talk about the final exam and all. We will do that. But does anyone have any questions on any of the content this quarter? And I know there's a lot. Now, as I would emphasize on, is guys, everything builds on each other. Unlike Gen Chem, don't look at each chapter as a separate thing, because they're really not. We study concepts and we use them throughout. So whatever you studied in chapter 1 works in chapter 7. It will work in chapter 20 also, for that matter. So try not to look at Ochem as this chapter, that chapter, so on and so forth. Try to look at it from the point of view of, do I understand hybridization? Do I understand polarity? Do I get resonance or a stereochemistry, or what is a racemic mixture or NMR? Basically look at it from the topic's point of view. And then don't forget it, because we need to use them over and over again. So final, let's talk about the final if there are no questions. Final is on Monday. Please note it down. It starts at noon, not 12:20. It's noon to 2 p.m. or 1:50 actually. It's a 1 hour 50-minute exam. Maybe we'll do two hours. That's totally fine with me. So we'll make it a 120-minute exam. Amayas, that reminds me, I need to speak to you before you go, because I may not see you after today till the final exam. So yes, it will be all multiple choice this quarter. 261 final is all multiple choice. Next quarter, it will be 80% multiple choice, 20% work that you have to show mechanisms and synthesis schemes and so on and so forth. But this quarter, your final is all multiple choice questions. I was doing the math the other day. I was looking at it. I think there were about 36 questions or 37, I can't remember, maybe 36. And they're all same number of points. So, and there were extra points. So 36, I think every question was about 3 points. So yeah, there were about 8 extra points in the whole exam as well as extra credit. Does that answer your question? Where did you go? Where did you go, Viola? I'm not seeing Viola.
Did she say Viola?
Okay. Can someone please make sure she gets this information?
She just left. She's the shorter.
Any other questions in regards to the final
I know.
exam on Monday?
Yes.
No?
For the final, do we have to show our work?
It's multiple choice. So you either got it or you didn't get it. Right? You just pick the best answer.
Oh no.
Yeah, it's gonna be.
Will the
That's not
final?
mine.
No. Okay. Ali is saying, could you talk about the
Because,
last?
you know,
Oh yes.
Yeah.
Thank you.
You can't-
Yes.
you
Give
can't
me a
get
moment
partial-
and I will. Thank you, Ali, for
partial
reminding me.
incorrect or
Will
not.
the
I thought it
final
was
be
multiple
more
choice,
heavy
but
on?
the-
No, not really. Final is truly going to be comprehensive, meaning that there's no intentional focus on any one part of the quarter. No. Unintentionally, if it happened, that's a different story, but no, there's no intention of doing that. Because, as I've said, all topics are related to each other. Unless you understand acids, bases, how do you do that? Unless you know resonance, how do you do this, so on and so forth. So, the answer to your question, I think, who is Amayas and Annika and Carrie, is no, there is no intentional focus on emphasis on any part of the course. No. Anything else final related?
When it comes to acids and bases,
When do we give the lab?
on the exam, will it
Monday.
be
Monday?
in more of the terms of what we recently learned, or would it be both? Like, will we encounter questions of acid and bases, what we covered earlier, or would it be everything?
Because again, learning is not this, I learned, it's not compartmentalized. And that's what I would encourage us to get away from. Don't compartmentalize your learning. If you learn something in English, should we be using that in chemistry? If you learn something in your calculus class and you have that skill that you can use to solve some problem in chemistry, should we not? No, right? So let's try and not compartmentalize our learning. Learning is learning. So the answer to your question therefore, Camilla, is everything. So focus more on understanding what does this mean? Because when you understand what an acid does, how it does it, why it does it, you can apply it anywhere. Have I answered your question?
Yes.
So, yeah, everything. Although I will not, of course, ask you questions Gen Chem related. I'm not going to ask you to calculate pKa's or pH's or use all those equations you learned in. No, we won't do that. But at least from the understanding point of view, we should know, okay, here's the job of an acid. Here's what hybridization does, or so on and so forth.
Have you guys listed questions for bio?
So like the exam,
Oh, wait.
is it going to be questions that we've had on like the previous exams? Same questions or?
Right, the questions are the same questions. There's only one question. I can ask it in different ways. It's a question.
But I think some topics are kind of brief and they were on the exams because they weren't really important. So are those not going to be on the final either?
Say that one more time, Dash. I missed that part. Say that one more time.
There were some parts, I think they were like super short sections and we didn't really have them on the exam. Are they going to be on the final exam?
In one. I'm trying to remember as well.
I don't have my backpack with me, but I swear I remember studying one thing and was on the exam.
Okay, I'm just going to cover my bases here. If we discuss something in class, if we didn't talk about something in class, no, it's not going to be that. If there's a section we skipped, we're skipping it. But if there's something we did discuss, We talked about it. Maybe we spent 10 minutes on it as opposed to 2 hours on it. But we talked about it. So then it's pretty likely. Yeah.
We're going to be able to take our tables and things, for
So,
IR
yes,
spectrum.
you can use your PKA, IR, NMR tables, but please, I want to say this again. Come third quarter, no, we can't. PKA tables, I think we should, because nobody memorizes PKA values. I don't memorize PKA values. Why should we memorize PKA values? But hopefully, by that time, IR and NMR, you got an idea of where things show up. So by third quarter, we need to be able to wean ourselves off of IR and NMR tables. But for 261 and 262, sure, use those, bring those. You want to use models during the exam? Go grab a model kit.
Use
Do
what?
it if you want.
Models.
Model.
I think that's actually a good tool to have, in my opinion, although it takes time to make models. But if you figure out how to do it more efficiently, do it.
I got my model.
Are there past exams? And the answer is no, I don't, because I recycle my work a lot. So I'm sorry, I can't share that stuff a lot, right?
Can't
I
share
don't
what?
really have that. However, I can guarantee that if you are working through every single question in the textbook, if you're working through every single question in the worksheets, there is no way you will understand the concept. If you've done 20 questions on hybrid, I take hybrid. If you've done 10 questions on resonance and you got them, you understand it then. Then we don't need sample questions or things like that because you got it, you understand. Blank copies of, oh, that's what you meant. Sorry, I probably misunderstood Amaya, Sonika, and Carrie. When you're saying blank copy, oh, there was also, somebody else also asked for it. From this quarter.
I was about to ask you that.
Do you mean from this quarter or?
What are you talking about?
Yes. Yes, I do.
This quarter.
I can do that. I can definitely do that. That is definitely doable.
I don't understand what. What are they
Do I
asking?
have access to them today?
Blank
Maybe
copies
I'll
of
do it
quizzes and
tomorrow when I'm back
exams
in my office,
that we
and
did
then
this
I
quarter.
can definitely do that. No problem.
Oh, I see.
Anything else final related? No, we don't need a Scantron. It is multiple choice, but it's only 36 questions. So, no, we don't need a Scantron. You can just mark
We don't
it on
need a
the
what?
exam.
Scantron. The Scantron.
Heck is
For next quarter,
is
I know
that?
you said that the final at the end of third quarter would be over all 3 quarters. Would the second quarter be over the first and second quarter?
In the sense that you can't discuss second quarter without concepts such as acids and bases, hybridizations, shapes, resonance, and stereochemistry and spectroscopy. We use those concepts. We will use these things in second quarter. So when we start discussing mechanisms, SN1, SN2, E1, E2, we will be using all of these things that we learned in 261. So from that point of view, yeah, because the concepts carry through. Does that make sense?
And that'll help
Yes.
us learn those concepts a little more.
In 261, we are establishing a foundation of some very fundamental concepts in Ochem. 262 onwards, we are going to grow on that and use them constantly again. So from that point of view, perspective, yeah, if that makes sense, what I'm trying to say. So,
Yes, thank you.
Yeah, and that is why the third quarter 263 exam is it's a national standardized exam that's comprehensive for the whole year, because again, these concepts are not in isolation. Spectroscopy is used all the time. Stereochemistry used all the time. All of these concepts
Is this
being
all the
used
people?
all the time. So
A lot of
that's
people
why
left.
it's all
I don't
one
see
big
Isabel.
course. Don't try
Yeah, they
not
probably
to
all left.
compartmentalize it.
I don't see Iman.
Anything else, guys? So that means whatever you learned here, please don't forget it during the winter break when you come back in January. Please, like, oh, what? Stereochemistry? What is that? Never heard of it. That would be fantastic. Anything else, guys? Okay. Then the last thing that we should talk about, two things I need you guys to do during the break. One is the lab, the first lab that we will do once we come back. We will actually have a lab in the first week, Jan 7th, I think. We come back on Jan 6th, Jan 7th is a Tuesday, we will have a lab. However, that lab is not from your textbook. It's basically a lab that I have created for us to get used to using the IR instrument and NMR instrument as well. So the goal of this lab will be, you will be given two unknowns, a solid and a liquid. You got to use, for both of them, you got to use IR, HNMR, and CNMR and identify what they are, the structures. Just like yesterday, you will work with a partner for this one as well, because NMR instrument unfortunately gets backed up a lot and it's frustrating. So we will do this in pairs as well. The goal I already told you, identify the structures and names of two unknowns based on IR and HNMR and CNMR. That's the goal. Procedure, don't worry about it because it's not in the book. I guess the only procedure is make prepared samples for spectroscopy and ran the spectra. Done. One sentence. I'm not kidding.
What?
I will need everybody over the break to watch the videos. And let me share my screen so I can show it to you. Which one am I referring to? To watch the videos that are posted on Canvas for, where is it? Yep, right there. IR and NMR videos. You already watched the IR video, so great, you're familiar with it. Here's the IR document, hopefully you've already read it, so you're familiar with it. Let's do the same for the NMR document as well. There are lots of bunch of commands there. You don't have to memorize it. Please don't memorize it. This handout is actually sprinkled all over the instrument room. If you've noticed, they're all over there. If you forgot a command, you can always look it up. But get familiar with it. Watch the videos, guys. Must watch the videos so that when you come back on Jan 7 for lab, you have an idea of what you need to do to run the NMR instrument. Of course, I will go through it as well with everybody to make sure everyone is also getting their hands onto the instrument and getting comfortable. But what I need everyone to do is use some of the time during the break to familiarize yourselves by reading the doc and watching the videos. Okay? Everyone, when you come back on Jan 7th in the lab, everyone needs to work on both instruments so that next time you use these instruments and you don't have a lab partner, you know how to do it. So you need to become more independent, of course. Initially, we'll start slow. I will hold your hand through things. But pretty soon I'm like, well, you've used it 4 times. You need to know how to do that. So
The IR is really simple.
does that answer your question, Ali?
If you
Does
wanna-
anybody have any
You
questions
guys want a
about the
sneak
lab?
peek of all the labs for
The
Ochem
first
too?
lab?
Yes.
Oh, that reminds me. The lab you guys did yesterday, you're bringing your lab notebooks Monday, right? For me to grade them. Isn't that right? Okay, cool.
Yep.
One more thing I need everybody to do. This is very important, actually. You might want to take notes so that you don't miss this piece. Let me know when you're ready. I can't see everybody's cameras. Can I have
Yes.
the cameras on just for a few minutes? I can make sure everyone is ready to take their notes down. Because I don't know, I just see black screens across. Okay. The next thing I need everybody to do over the week, over the break, what, 3.5 weeks break or so? Do something fun.
Write it
That's
down.
nice. Spend some good time with your family and friends. Do not be stressed out. Are you writing this down? Are you ready? Because we forget to do that. This is a very good break because when you come back in Jan, you won't get a break till June. So make use of this break and actually have a break. Okay?
Oh, Lord.
Promise me? Perfect. That's all I have to say. Of
Pinky
course, I'm gonna
promise.
see
How do you say
guys.
pinky promise?
But, sorry, I need to sneeze. Just a second.
Thanks.
Oh, gone. I hate it. Gone. Okay, cool. Then that's all I have for today. If anybody has any questions, of course, please, I'm here. Hang back. If not, then I'll be on campus tomorrow. Otherwise, I'll see you guys on Monday at noon. Take care, everybody. Stay safe.
Thank you, you too.
Bye.
Have a wonderful day.
What? You too. Have a wonderful day too. Emma. Can you hang back, Emma, so you and I can talk?
Do we, is that it?
Sumita, did you say I left my notebook in the lab room?
Unless you have
Yeah,
any
but
more
I have it
questions
in
for
my
me.
office now.
I'm sorry?
Okay.
I found it.
Yeah. So if you, I should be in my office till about 9:50 in the morning, and then after 2:30, around noon, I should also be in my office. So-
Okay.
Or I'll leave it in this basket outside my office door.
Okay.
I can leave it in there, and you can pick it up from there.
Okay. Thank you.
And I have yours as well. I will finish grading it. I will leave your notebook also in that wall basket outside my office door, so you can take it tomorrow. Is that okay?
Non-stop until June.
Do I
don't know
have
if can
office
take
hours? Yes,
these.
same as on the syllabus. I mean, yeah, on the syllabus. Yeah.
Oh, she has office
Okay.
hours tomorrow. That's
Quest-
good.
Yeah, I'm gonna be there.
Okay. See you all then. Have a wonderful rest of your day. Take care, everybody.
And make sure to hang out with your family after the break too.
Yes, during the break. Absolutely.
During the break.
Friends and family.
Okay. Oh, Lord.
So, I mean, if you wanna,
So of who's that? Is that, you didn't do, did you do Ochem last time? You did Ochem 1
and two.
and 2?
Mhm.
Oh, and then you had to repeat. Why?
So I went through Ochem 1, passed Ochem 1, went through Ochem 2 and failed Ochem 2. I had a lot going during that time.
But you did not fail Ochem 1.
No, I passed Ochem 1.
And, but you decided to do it again for a better grade and to catch up for Ochem 2,
Just
right?
for the
I would do the same thing.
just for the benefit of like, I need to know this with your girl.
Because
I'm thinking I might-
If I had waited for Ochem 2, I would have probably,
Flunked it again.
Yeah, because it's hard. Yeah, I don't know if I'm coming.
That was
I probably going. I kind of want to take a pause and start in fall again.
that was
This has just been too much.
no. While I was taking Ochem 2, I was
I need
was
to tell you
working
about this.
and all that.
Oh, let me.